A warm welcome, please, for Professor MacPherson from the University of Warwick, who's going to talk about the wonders of element number 6, carbon.
Okay.
So, thank you very much.
Yeah, thank you very much, Mark. Hopefully everybody can hear me. I've just actually noticed my cat's walked into the room, so I hope she's going to behave herself. So if not, she's going to get booted out. I know it's difficult. You've all been at school, you've been learning all day. So I'm going to try and keep you entertained, hopefully, by talking to you about an element that is very close to my heart because I've been researching on it for the past 15 years. And really, hopefully you can see the versatility of working with this particular material. Okay, so when I was a young undergraduate student, I remember I had a professor who, when the first day we came into the undergraduate labs, he said to all of us actually, you know, what's your favorite element? Because what he wanted us to do was not just be learning chemistry for the sake of it, but to really think about the properties of different elements and to think about which element actually was more interesting to people. And at the time, I can't remember what I said, but now if I'm asked, because of the more I've done in chemistry, for me, definitely it's carbon. And if you go to the Royal Society of Chemistry website, you'll see that carbon is actually listed as the king of the elements. And this particular gentleman here, Martin Polyakov from Nottingham, who has given talks in this series as well, has recorded some fantastic individual YouTube videos on each particular element in the periodic table. So you can go to his videos and he's got some really interesting stories for each of these different elements. So I would encourage you to think about what's your favorite element and to then go and look up Martin Polyakov and his YouTube story of that element. So this one is the web link to carbon. I'm going to give you a bit more information than what you'd find in Martin's YouTube video. And actually he has done one on aspects of carbon, including diamond, which I'll talk about at the end here. Okay, so if you take carbon, let's consider how many electrons there are. Okay, so we've got 6 electrons. We have 2 in the inner shell and 4 in the outer shell. And they exist in s and p orbitals. So I'm not sure how much you've done on shapes of orbitals and orbital mixing. But for now, what I just want you to think about is these 4 electrons, they're bonding electrons in these 2s and 2p orbitals. We need to think about the shapes of the orbitals that can arise. And what happens is you get hybridization. So you don't get an s and 3 p's existing by themselves. What happens is they mix. And there's various ways in which the orbitals can mix. And these will give rise to the different bonding configurations. So if we take 1s and we mix it with 3 p's, we can get what we refer to as sp3 hybridization. And this is what the shapes of these orbitals look like here. And when you put them together, actually, 4 of these, they give this beautiful tetrahedral symmetry. And so for carbon, you pop an electron into each one of these lobes here. And you can imagine another carbon atom coming up and having an electron overlapping here. And what you end up with is in sp3 bonding, if you can see, is this network of very strong, short covalent bonds. And we'll touch on this later, but this is actually the structure of diamond. And it arises because of the mixing of 1s with 3 p's. Now, there's other ways you can mix. You can mix 1s with just 2 p's and you leave that remaining p orbital by itself. And when you do that, you have something called sp2 hybridization. And the resulting orbitals here are almost in a planar configuration. And you can pop an electron into each one of those orbitals and you have a remaining electron in this, what we call unhybridized p orbital. Now these are fairly flat. And so when you put them together, you get these like flat structures or almost flat. And actually the most common form perhaps that you may have come across already is the benzene ring. So we have 3 of the electrons per carbon atom involved in bonding. And we have this 4th electron here popped into one of these unhybridized orbitals. And this is where you get this electron delocalization. It can move across the bonds effectively. And this gives it properties such as, when you start to build up these benzene rings, property of conductivity. In that diamond lattice, all those electrons are held very tightly in covalent bonds. And so we're going to talk about this material later, but you can see all these benzene rings effectively come together to make graphene. Now, when you layer the graphene, you get the material graphite. Now, as I said, the bonding is strong in these sp2 layers in the sort of XY direction, but it's weak in this plane, the Z direction. And this is why these layers can slip over each other. But you have very good conductivity in the planes. And so we'll talk about how people first made the discovery of graphene, because this is something that most people are used to working with. Now, if I go back to this, you'll see that all my pictures to date, and whether I'm putting something like this up or showing you something like that, it's all single atoms. So if I want to really look at structure determination at the ultimate level, I want to be able to have microscopes that can identify single atoms and show me where they sit. Now, if we start to look at microscopy, if we think about microscopes that you've come across, you're probably thinking about an optical microscope that you might have in your school labs. Now, an atom, if we look down here, the diameter of an atom, let's say it's about 0.2 to 0.3 nanometers. Okay, this is very, very small. Nanometer is 10 to the minus 9 of a meter. Human hair is about 100,000 nanometers. So if you want to use an optical microscope, what's the smallest thing it can see? The smallest thing it can see is actually limited predominantly by the wavelength of light, because this is what happens in an optical microscope. You have light coming through and it's focused with glass lenses. Now, 400 to 700 nanometers, if that's the smallest thing I can see, there's no way I'm going to see an atom. So how can we get moved forward to see atoms? And this is where this talk is also going to be a talk about Nobel Prizes. This is where the first kind of Nobel Prize comes in, and this was for the invention of a microscopy technique called electron microscopy. And this occurred back in the 1930s. And people said an electron has wave-particle duality. It has a mass, and it also has a wavelength. So if wavelength of the source is limiting, let's go to smaller and smaller wavelengths. How can I do that? Let's use electrons, and let's change the energy of the electron, and we can start to change the wavelength of the electron. Now, instead of having glass lenses for focusing, what you have in electron microscopes is electron beams, and you have magnetic lenses. And you can actually, by pumping enough energy into the system in which you eject the electrons out, you can get to single atoms. Now, we're very lucky. At Warwick, we have some of the most powerful electron microscopes in the world. And when you do this, you can see down to effectively single atoms. This is a sheet of graphene imaged in one of these transmission electron microscopes. And I really want you to think about the scale of this. This is allowing us to see the fundamental building blocks. Now, if I talk to physicists, they'll say, oh no, you need to go, the atom is, there's loads of things inside the atom that we're interested in. But for me, I think it's amazing that you can start to see atom structure on an atom by atom level. This is even done in my own work, where we're looking at taking diamond surfaces and we're starting to try and make the smallest metals we can, and that would be single atoms. And so here, these are literally single atoms of gold, which we have fabricated on top of a diamond surface. So this is from my own research work. Okay. So I just want to tell you about another Nobel Prize winning technique here. This one was awarded the prize at the same time. So even though electron microscopy was invented back in 1930, when they decided to give a prize for microscopy, this was the Nobel Prize in Physics in 1986, they awarded it as well, backdated it effectively, to the people who also developed the electron microscope. But these guys didn't say, okay, I'm going to use wavelength and I'm going to use lenses. They thought out the box. They said, let's come up with a completely different way of actually looking at the surface of objects and getting down to atomic resolution. Now, although it's coming back in record players, okay, it's probably retro now, the concept of a stylus going over grooves, or for people who are reading Braille, a fingertip reading bumps on a surface. It's a similar concept. you take a very, very sharp tip, right? The sharpest one you can get. So there's just a single atom at the end of that tip. You have your rows of atoms on the surface. And what you're going to do is you're going to bring that tip up really, really close, and you're going to monitor some form of interaction. And that interaction is going to give you information on the atom structure. So in the technique that they invented here, and one of these people was from IBM, because they had a huge interest in molecular electronics, how to make electronics at the smallest scale ever. What you have is a form of quantum tunneling. So this gets us into the physics regime. Basically, I take two surfaces, this tiny metal tip and this tiny metal surface. Well, actually, the surface isn't small. The tip is very small. And you bring it so close, but I'm not touching, you get an effect called quantum mechanical tunneling of electrons. And this gives you a current. I haven't got time to go into details here, but it's a really fascinating effect. And what they're doing is they're monitoring the current that flows at that tip, and it's giving you information on the atoms. Now, not only can you see atoms, but in this tip, what's really neat, you can manipulate atoms. I can pick atoms up and I can move them around. And so here you can see the production of the word, the kanji symbol for atom. So in atoms, so iron atoms have been manipulated on a copper surface and moved to create this word. You can see also that people have done this for the IBM logo, and this is phenomenal. This is truly atom scale engineering with these very precise tips. So this is seeing, so not only seeing, but manipulating atoms at this level. So this is truly nanotechnology. Okay, out of this technique, because that technique only works on metal surfaces, because you have to have a current flowing, so you have to have a conduction path. And so people wanted to develop this form of microscopy for surfaces that were non-conducting, especially in the biological region. And so people, instead of measuring a little current flow here, they measured a force. So again, thinking about forces between atoms and what controls this. Anyway, you put a little force sensing cantilever onto the back of your tip, and now you can start to get these spectacular images of biological structures. So here, this is the helical twist in DNA. And here, this is showing you a light harvesting complex found at the back of the eye. And they're taking it apart, and they're imaging what these structures look like using this little tip that's scanning over the surface and monitoring these topographical changes. But just think of the scale. This is like, you know, an atom is 0.2 nanometers. So this is phenomenal. So in microscopy, we're really lucky in science that we have such powerful microscopes that let us see down into the nanoscale dimensions. And actually, I love microscopy because when you start to zoom in, you see the most fascinating of structures. Okay, so let's go back to carbon. And let's start to think about the different carbon structures that have evolved and how these have embraced what we call nanotechnology. Because when you think normally of things like graphite, you think of it being, you know, bulky material, macro scale. The structures I'm going to talk to you about are very much on the nanotype scale in terms of one dimension is of a nano size. So let's start with the first Nobel Prize for the carbon structures. And this was awarded in chemistry over 20 years ago now. And I remember at the time when this came out, because at the time people had just talked about carbon being graphite or diamond, and then this discovery came to fruition. Unfortunately, the people who made these discoveries, I think, are no longer with us, and some recently passed. Harry Kroto was a British professor. And actually, this story that I'm going to tell you, again, is about, you can get a Nobel Prize by not setting out to discover this. You can discover it like along the way, but it was part of your journey to find out something else. But instead, you discovered something that was far more interesting. And even in my own research, you know, I set out on a path to try and do something. And I find that actually I found something that I never thought about, and it's just come up in the experiment. And this is what happened here. But actually here, they won the Nobel Prize for it. So let me tell you what they were trying to do. So Harry Kroto was an astrochemist, astrochemist stroke physicist. And he was interested in the interstellar compounds that exist. So he was interested at the time, this is a giant red star, is what would be the sort of carbon structures that would be found in this kind of environment of these sort of objects. And so obviously you can't go up and study that. You have to try and recreate the conditions. And he was put in contact with the Texas team in Houston, who had facilities that could recreate sort of the environment and try and produce these carbon-based structures that might be existing around these giant red stars. And so they coupled their chamber where they were creating from these carbon molecules to something called a mass spectrometer. Now, I think some of you should have heard about mass spectrometry. It's a way of characterizing structures. You basically blow your compound apart and you get molecular fragments and you analyze as a function of mass. So what they did is they took a graphite block and they were recreating conditions, and then they put it into the mass spec. And what they found is they got this really sharp peak here. And this peak was the number of atoms of mass 12. This is carbon. And they found that they kept finding 60 atoms of carbon featuring very heavily. So the question was, well, what kind of structure makes 60 atoms, and why, if it was a chain, why 60? Surely that chain could be any kind of length of carbons. Why just something so unique about 60? And this is where they had to really start to think, is it shaped in a way that it terminates at just 60? And this is where they went to actually architecture, to think about, well, how can I arrange 60 carbon atoms? And this was quite a famous architect, Richard Buckminster Fuller, and he was designing geodesic domes. So how do I create these dome structures? And actually it's the same way you do a football. And he'd shown that you can take hexagons and pentagons and you can make these balls. Now, if you count up the number of carbon atoms in this ball structure, it's 60. And what they thought was the only way that we can be arranging to have this unique 60 atoms is to make a sphere of carbon atoms. And this was called, after Richard Buckminster Fuller, the fullerene. And as I said, I put here serendipity. They never set out necessarily to make a new form of carbon or a new way of arranging the carbon atoms. They thought they were looking for these long chain carbon systems, but they found the Buckminster fullerene. Need to go away and prove it. So as I said, I've shown you about microscopy now, and you can take, this is a TEM image, don't worry for now, they've put things on the end of these things. But you can start to see really beautifully in the transmission electron microscope, so in these sphere structures. And now people can say that they can make a whole range of different molecular type spheres of different sizes. But this C60 really kicked off the field. And as I said, they were awarded the Nobel Prize for this. Now, at the time, it was quite revolutionary to think about this, but then people started to think about, well, how can I use it? And these are some of the host of applications people have tried to work with. So, photovoltaics, how do we take the sunlight and convert it to electricity? How do we scavenge for antioxidants? So free radicals are thought to be implicated in cancer causing, and then electrical devices. And I'll come back to this. There's a lot of applications where people are starting to use these sphere structures of carbon. Now, if you produce these balls using these techniques where they were sort of firing lasers at graphite blocks under these certain conditions, what they also said is, well, if we can identify it in the electron microscope, these spheres, have we formed any other really cool structures of carbon that we never thought would exist? And then what happened was people started to do more and more electron microscopy. And this is a very famous scientist, Gima, who was looking at the deposits that were left behind, these sooty deposits. He was putting them into his electron microscope and he was starting to see, what would I find? And actually here he found another form of a carbon. Actually, instead of a ball, what he was finding was these tube structures. And actually in the ones I'm giving you here, this is a single walled tube structure, and this is a multi-walled tube structure. And these again were sort of new configurations of how to arrange carbon atoms that hadn't been known about. They'd always existed, but people just hadn't found them before or worked out what conditions to produce them. Now, when you write a scientific paper, this is when you do your experiment, you write the results, you get it reviewed by a community, and then it gets published. People, if they read your work and they use that work to help them do their experiments, they do something, they cite your paper. Now, a paper that's probably well cited is something that's had 100 people maybe look at that paper and be influenced by it. This paper in 1991 has been cited over 52,000 times. This is a phenomenally influential piece of work, and all these original carbon structure work has really influenced the field tremendously. Okay, so what are we doing? How do we make a tube? Well, the best way to make a tube is simply, you think of it as wrapping up a graphene sheet. You wrap up the graphene sheet, and what you do to close the tube is you cap the end with 2 halves of a buckyball. And these are really interesting carbon shapes now. So we've talked about the buckyballs. We're now onto the nanotubes. I'm just putting this up because actually, when you look back through Ejima's work, where he was looking at different things that you'd find in effectively like carbon soot, if you look back, he'd almost seen these like carbon buckyballs back in the early 80s, but hadn't really realized the power of what he'd got. And obviously, electron microscopy has increased in resolution tremendously since then. So these forms of carbon, as I said, have been around for a long time. It was just they were waiting to be discovered, as all discoveries are really. Okay, so we can grow nanotubes. We do this in our laboratory. We take metal nanoparticles. So these are tiny particles of metal, and they act as catalysts. So remember, a catalyst can speed up a reaction, but isn't going to be changed itself. And we flow through with a carbon-containing gas. So this could be methane. And this methane breaks down, and it starts to rearrange itself. And it starts to rearrange itself around that nanoparticle and grows out into a tube. Now, people have done some really funky things with nanotube growth. And you can you can grow all sorts of structures for carbon nanotubes. So this is John Hart from MIT in the States. This is his nanotube garden. Every single one of these structures is a carbon nanotube that's either been grown together. So most of these are all grown together to form like quite dense networks. But I just thought this was a really nice image showing you different ways. You can see here that these are all individual carbon nanotubes that are forming these sheets and stuff. So none of these are an isolated tube. They're all nanotubes that have grown together into these different patterns. I can show you some other images from our own lab. You can see here in a bit more detail what I mean about when they grow together. They make these very thick conductive mats, and you can see them. You can pull them apart, and each one is made from these tiny, tiny nanotubes. And then you can do it in a more precise way. So you can grow these defined blocks, and people are trying to think about using these in electrical circuitry as interconnects, so connecting one component up to a next, because these carbon structures are conductive. So this is us aligning our nanotubes, and this is me growing a single nanotube here. So there's the catalyst particle I told you about that initiates the growth, and then this nice carbon nanotube results. Okay, so what can we do with nanotubes? Right, so people are thinking about using them as making the smallest ever electrical component. Now, in your devices that you use, your laptops, your mobile phones, one of the key electrical components is something called a transistor. It's like a switch. It switches on and off. And if you want your devices to get smaller and smaller, your electronics has to get smaller and smaller. And this is what Moore's law was all about, in terms of how we have to shrink down our systems. And this is why all the big electronics industries are really interested in these carbon structures, because they think that they might be ways of improving electronic performance. So you can go and look at schematics on front covers of very prestigious magazines such as Science, where all the best research is published. And it's really easy to draw a picture or a schematic. And this is the problem with nanotechnology, is they draw a picture and it looks really easy. So what you have here is you have your nanotube, and you've got like these things here are like 2 crocodile clips to either end of the nanotube, and I'm going to pass a current through. And these nanotubes, as I said, can act as switches, so they'll switch the current on and switch it off. Drawing a picture is really easy. Making the device is much harder. And so to make these devices, you have to go into these like clean rooms where you have very precise engineering, but at the nano to micro scale, there can be no dirt or dust because the dust particle is way bigger than your nanotube and it's going to really impact your device. So these are all like electrical wires on your device. And what you need to do is between two of these electrical wires is you need to put or somehow grow or place a nanotube. And as I said, that's one of the challenges in all of this is how do I put that nanotube into a precise location on such a tiny scale. We have had to go at this ourselves. So this is an atomic force microscope image where that tip is scanning over the surface. And you can see these are the two metal contacts. They're like the crocodile clips connecting up the wire. And you can see here, this is a single nanotube. And then this is what I mean about a gate. No current, current's on. Current flows, current off, okay? Other things I do is I look at using them as sensors. I sense species, either in solution or predominantly in solution, but sometimes in the gas phase. And I use these mats here of nano electrodes, these nano tubes, to do this sensing. Just one application is we work with colleagues down at the Imperial College London, and we're interested in sensing these neurotransmitters, dopamine and serotonin. So these are important signaling molecules, and they can be oxidized or reduced. And we can detect the oxidation or reduction of these species by measuring a current at our nanotubes. And so we can work with colleagues who look at monitoring these signaling molecules in the brain of people who've suffered significant brain trauma. So a lot of research is carried out with hospitals. So there's big collaborations between universities and hospitals in order to take the research that universities do and help in the hospital environment. So we work ourselves with our local hospital in Coventry, for example, developing different types of sensors. Okay, so I talked to you about AFM, which was this tip, and it scans over a surface. Now, the technique where I showed you the single atoms, they can get their tips really, really sharp. So you have just one single atom. These tips that are used in this technique, it's quite hard to get them really small or small enough. So you don't actually ever see atomic resolution. So this is this tip has a radius here of about up to 20 nanometers. And remember that a single atom is 0.2 of a nanometer. So this is not small enough yet to see single atoms with this technique. The other technique was, and it's just, I won't go into details, but it's just different ways to make sharp tips. However, what we were doing was putting, and this was work that was initiated back in Harvard by Charles Lieber, we were putting these single-walled nanotubes onto the ends to make them even sharper. And this was, so you can see here, if you have a feature like this, if you have a very sharp tip, you can trace it really nicely. If that tip gets bigger, you have what's called convolution. So you can't resolve the two features. So we come along and we take our tip and we pick up a nanotube onto it. And can you see here, this is my normal tip, and then this is with a nanotube on the end. And this is now going to be my new imaging point. And you can see here how you've improved the resolution compared to something here. So I really like biking, and I actually have a carbon fiber bike because it's lighter, it goes faster. And up to, previously people were putting in graphite into the polymers to make the bike material in order to give them this durability, but lightness associated. Now you can buy bikes that either have graphene in them, as I'll talk about later, or carbon nanotubes in them. And they're deemed to be a better source of carbon in terms of making these sorts of, things like tennis rackets or bikes or stuff like this. So this is also a way that people are using carbon nanotubes. Okay, let's switch. So that's single-walled nanotubes. Let's switch to a new one that got the Nobel Prize, and this was the most recent Nobel Prize for the carbon material, and that was for physics in 2010. And this is for graphene. Okay, so I put it the new kid on the block. Okay, so this was awarded to 2 people who are at the University of Manchester, actually. And the government has invested heavily in graphene work now. And there is a graphene or 2-dimensional material centre set up in Manchester based on the work that came out of the labs of Andrei Geim and Novoselov. Okay, so graphene. Just to remind you, if you think about graphite, it is layers of graphene. And so how did people produce the very first graphene material? And that's one single layer. Well, believe it or not, what they did is they took graphite. So this is a sheet of graphite, which has got all the layers together. They took sellotape and they basically spent a long time trying to just peel one single layer of graphene off. Now that sounds like a horrific job. And I think talking to people who've done this, it's one of those things that is incredibly difficult, and you have to have a knack how to just peel one single layer of graphene from that block of graphite, but it is possible. And this is what all the original work was done. So this is actually a single layer of graphite, which is called graphene. And that's the atomic force microscope image of it. And you can image the height difference here, and that correlates with just a single layer of graphene. And then what people were doing is this also has very interesting electrical properties. So again, this was, quite crude in the very early days of when they were doing this. This is them trying to put these like crocodile contacts on in order to try and connect up that graphene that they produced and pass electrical currents through it in order to show the really unique electrical properties of this material. So this was, as I said, this was a real feat of kind of hard work to produce the graphene in the first place, then connect it up, and then start to show some of these unique properties. You can grow the graphene now in a very similar way to the way that you grow the single-walled nanotubes. So I said that you would have an oven system, and you would have a carbon source, and you would have nanoparticles for the nanotubes. Okay, all we're going to do here is we don't want to grow a tube from a nanoparticle, we want to grow just a flat sheet. And what we do is we use a metal catalyst, but it's in a sheet form. And if you use particular metals, you can grow, so you just grow one single layer of the graphene. Some of the metals will promote multi-layers, but if you use something like copper, you will grow just a single layer of graphene. And this is really useful now because dependent on how big your copper sheet is, you can grow large volumes of graphene. And people have looked to how they can scale up this process, right? Because nobody's ever going to win by having to peel off, right, little bits of graphene and try and do work with it. If you want to make anything into a commercial activity, you've got to have a way of scaling what you're doing. But also what you have to do is take into account cost, because nobody's ever going to want to work with a material or device that's too costly to operate. So this is a device that my ex-PhD student, he now directs a company, and they were producing their own graphene CVD growers. And these are some of the applications. There was the graphene light bulb. As I said, graphene's being integrated into bikes now, into tires, into tennis rackets. It's also being used in electrical devices. Okay, but just watch this space. See what you Google graphene, see what's coming up for its latest uses. Right, so I think what I want to sort of finish on is I've talked a bit about already single-walled nanotubes. I've talked about fullerenes, but now, and I've talked now about graphene. So these are all carbon atoms that have been what we call sp2 hybridized. Okay, so you've got one s orbital mixing with two p orbitals, and you have a p orbital that's left unhybridized. So you have electrical conductivity associated with all of these forms of carbon. And you have strong bonding within these networks here. But as I said, for graphite, you don't have strong bonding between the layers. This is a strongly bonded tube. It actually is quite flexible. And that's another advantage of it. And there's strong bonding here. But what about diamond, right? So diamond is completely different. It's got, each carbon is bonded to 4 others. It doesn't have any electrical conductivity because all those electrons are held bound in those in those strong covalent bonds. And you can build these phenomenally strong networks. The question is, diamond has lots of really interesting properties. So it's very strong. I'll show you some others as we go along. But how do we grow diamond? Because for all of these applications, as I've shown you, you've got to have methods for growing the carbon material for that carbon material to be useful. So when I say diamond, and I do a lot of work on diamond at the moment, we make lots of devices out of diamond, especially in sort of sensor applications. So for environmental sensing, medical sensing. But when you say diamond to people, this is immediately what they think about, these sparkly gemstones. What I want you to notice is the colors. You can get transparent diamond, but you're also going to get colored diamond. And what I'll talk to you about as well is why is the diamond colored and how does that change its properties? I mean, you should already kind of know that if something is colored like this, it must be absorbing light in the visible region. And if it's not here, then you must have changed the electronic structure in some way. Okay, so we'll come on to that because it's a really interesting property. Where do I find diamonds? Okay, so first of all, most people, if they're thinking about these diamonds, they think about this and they think about naturals. So natural diamonds are mined. And what I've put up here in the map is just areas of the world where you are likely to find diamond mines. Now I'm going to show you, and this is quite a fun thing to do actually, if you go to Google Earth, is go and look at a diamond mine on the Google Earth maps. So let's take one in Russia. So can you see here, this huge hole in the ground is where they are mining, going into the earth in order to mine out the diamond. Now this entire city has arisen purely because of that diamond mine. And that's phenomenal. So diamond mining is a huge industry, and the amount of diamond that's recovered, if you think about it, is actually small, but the cost is high. And this is what generates these huge activities around these mines. You can see here at this Russian mine, they've even set up their own airport in order to, once the diamonds come out, they've got traffic coming in and out. And this is just another side view of it, just to give you an idea of the scale. These are the sort of the places where people are living and working at the top here. And this is the mining activity down here. Okay, so how does diamond form? How is it formed in the earth? Well, if you think in terms of a recipe, what we need is we need extreme high pressure and we need high temperature. So it's formed right down deep into the earth. And one of the things is sometimes it's a misnomer that it takes a long time to form diamond. It doesn't necessarily. The time comes from actually trying to get that diamond actually exposed up onto the top surface of the earth where we can find it unless we mine it. So volcanic eruptions or volcanic pipes are one way that we can see the diamonds coming out. The other way is to mine, okay, but that's costly. So that's how diamonds form naturally. Now, because diamonds have lots of really interesting physical properties, so as I said, I'm going to go through what these are. There's a need to be able to not have to mine diamond because it's so expensive. What we prefer to do is actually grow diamond. And can we grow diamond in a laboratory? So one way to grow diamond in a laboratory is, can we mimic the high pressure, high temperature growth conditions in the earth, but can we do it in the lab? And actually, yes, we can. So as I said, it's like a recipe. What you need a carbon source. The metal, again, is like the catalyst for allowing this breakdown of the carbon source or allowing this process to evolve. And we often seed it itself with diamond seeds to keep the reaction going. And this is where it gets fun. We need to set up in the lab, so you have to be really careful. This is done in very controlled conditions, and there's lots of diamond labs around the world that are doing this. High temperature, and then we have phenomenally high pressure, 55,000 atmospheres. To give you an idea of what that is, imagine taking the Eiffel Tower, turning it upside down and pressing it onto a Coke can. That's the same sort of pressure to do this. However, people now have realized there are far simpler ways to grow diamond and with kind of better control in terms of if I want to change its physical properties. And actually, I said the way to grow nanotubes and to grow graphene is to use these hot ovens. And we do exactly the same here, except we're also combining it with microwaves to produce these high energy plasmas. We have a carbon source, we're going to pump methane in, we have hydrogen gas, and we have a diamond substrate to grow off. And if you look here, you can see that the substrate temperature is much lower. The plasma temperatures, because we're using a microwave to generate a plasma, is high, but the pressures are much lower. So this is a more manageable system. And if I go to this video here, this is the diamond surface growing. So what these are hydrogen gases splitting into hydrogen atoms. This is a methane. So I need one of those CH bonds to break. That hasn't broken there. Okay, here's one that's got a missing hydrogen and it's going to stick on the surface. And this one's going to stick on the surface. And what has to happen is hydrogen atoms need to come along and pick off these hydrogen atoms on the bonds, and then they can have these CH radicals adding. Okay, so this process will happen layer by layer by layer. And this is what's happening now. There's lots of growth labs, lots of companies set up who are growing diamond as we speak for different applications. So why grow synthetic diamond? As I said, lots of great properties of diamond. And if we can grow it, we can control those properties. So we could decide to grow the diamond as thick as we want. We can grow it with particular properties. We can grow it with particular color. Now, when this stuff grows, it doesn't grow how you perceive the shape of a diamond to be, right? It grows as like a slab. That shape is because it's been polished at those particular angles. And even the diamonds that are removed from the earth don't come out looking like that. They're rough diamonds, they're raw diamonds. They need to be polished to give you those right angles to make that diamond sparkle. Okay, so these are all diamonds that have been grown synthetically. So let me show you some of the applications. So the first one that everybody knows is we've got this incredibly strong, rigid structure, right? Diamond is the hardest material going. So it's used hugely for cutting and grinding and actually digging into the earth, right? Because of these properties. And this is just showing you some machining with a diamond blade or a diamond tool. Now, if I used an inferior material to that, the machining rate would be significantly lower. But let's think about other properties of diamond. Okay, diamond you can see through, it's transparent. Okay, there is a region where it does absorb. But what's important is it can actually pass through infrared light, microwaves, X-rays, ultraviolet, gamma rays. And because of its strong properties, passing, especially at these high energy wavelengths up here, you don't damage the diamond. And this is really important. And so diamond is used for many different laser windows, okay? Because I can pass high energy through the diamond and I don't damage the surface of the diamond. So there's lots of applications where people are using this now. I've seen applications as well, even on like for mobile phones. People are using, people scratch their phones, they drop their phones, stuff like this. People are using thin films of diamond as a scratch resistant, mechanically hard surface. Okay, thermal conductivity. What is it? Basically, it's the ease at which heat can pass through a material. So obviously this is high, this is low. What's the thermal conductivity of diamond? Okay, just show you. So if we look at how diamond compares to other materials, and copper is always thought to be extremely good, diamond has the highest known thermal conductivity. So this is interesting. It's got the highest thermal conductivity, but it's got minimal electrical conductivity, right? The two don't necessarily correlate. Why has it got very high thermal conductivity? The heat is being transferred through a lattice by vibrations. And what the advantage of a diamond lattice for passing heat through is it has very short, very strong bonds. So the heat can pass really nicely through that lattice. Okay, so it's got phenomenally high thermal conductivity. That means I can get heat out really quickly of any device. And so what people are doing, remember I talked to you about if you want, smaller devices, smaller phones, smaller laptops. What's one of the big problems when you're working with your laptop? You got it on your lap, it gets hot, right? Heating issues, people have to build fans in. Well, if we can back all our electronic circuitry, which is giving out this heat, onto diamond, which acts as a heat sink, we can start to have a natural coolant in there. We can use the heat in some other way, which is energy efficient. So this is a really nice area of research that's going on at the moment, is can we work with diamond-based electronics? Okay, diamonds, I showed you, are colored. So why are diamonds colored, and how can we benefit from the fact that diamonds have different colors? So some people might say, okay, I like the fact they've got different colors because they're pretty and I prefer a blue diamond to a pink diamond, right? But actually scientifically, they're colored for a reason and we can use those in applications. So why are they colored? Colored diamonds means they've got impurities or defects in them. Let's look at the periodic table again. We've got carbon. Either side of carbon, you have boron and nitrogen. So if I'm going to kick out an atom of carbon from the lattice, you can only get similar sized atoms going in, right? Because otherwise it's just not going to work energetically. So in terms of impurities that might form in a carbon lattice of diamond, you're going to be looking at either boron or nitrogen. You can also get defects where you basically have a missing carbon atom, and that's quite important as well. So if I start to replace in my lattice of carbon atoms, one boron, I will turn my, so if I think it's 1 in at least 1,000, sorry, I think, let me get my numbers right. 1 in about 100,000 or 1 in a million is enough to see a very small color change from transparent to light blue. If I now replace 1 in 1,000 carbon atoms with boron, I basically have a black diamond. So if you see blue or black diamonds, it's because we have trace levels of boron sitting in the spaces where carbon atoms should be. And what you've done is, if I look at an energy diagram, is I've introduced new energy levels by the presence of the boron. And that's meaning the light is now interacting in a different way to how it was when they weren't there. If you put nitrogen in, your diamond goes yellow, and more diamond makes it kind of a darker yellow brown color. If you have defects, missing vacancies, you go pink. So all these colors tell me, I can look at a diamond and I know exactly what's going on in terms of the chemistry or the physics of that structure. Why do I care? Because I can do really interesting things. I can take, if I have boron in my lattice, I introduce new energy levels, right? And I can take my diamond, which was completely insulating electrically. I couldn't get any electrons flowing. And I can suddenly start to make electrons pass through my diamond. So blue or black diamond is conducting, right? It's like graphite. White diamond, transparent diamond, sorry, is insulating electrically. Let me show you a natural diamond. So this is a natural blue. Okay, 150 to 190 million if you've got some spare cash. This is in the, oh gosh, I always forget the name. I've seen this diamond actually because we know the people who curate the exhibit in the museums in Washington. This is a natural blue. So this would have been grown in the presence of boron impurities. And this has got a really fascinating history, actually, if you want to look it up. Over the years, people have lost lives over diamonds, unfortunately, for many different reasons. And this one has actually even changed shape over the years because people tried to disguise it. But that's a natural. And then this is what I would use in my lab. This is all black diamonds. So I have lots of diamonds lying around. They're all black because I like to pass electrical currents through them. The final application I'm just going to quickly show you is if something, and this is being, a reason I put it in, it's quite complicated physics behind this, that my physics colleagues work in this area. If you have a nitrogen atom in the lattice, and it sits next to, so this stands for nitrogen, it sits next to a vacancy, so that's a missing carbon atom, you get some really interesting effects going on. And people are using this now in quantum technologies or quantum computing. I haven't got time to go into this, and it's not necessarily my area of expertise. I should get my physics colleagues to talk to you about this, but let me just show you that because of this defect present in the diamond, if you shine green light into that diamond that contains this, red light pops out. Okay, and what you can do is I can manipulate it even further. If I put a magnetic field on, I can switch that red light off. Okay, so I can start to play around with this at truly an atomic level. So people can use it for sensing magnetic fields, these diamonds with these NV centers in them, because you have green light coming in, I have red light popping out. And what happens is when you hit a certain microwave frequency, I can switch, and associated with magnetic fields, I can switch the red light off. Okay, so I won't go into too much detail, but just to give you an idea that when you see something like diamond, most people naturally just go straight to thinking about a gemstone. And as scientists, there's so much more to these materials than that. And diamond is particularly fascinating to me because of all the ways you can change its properties. You can change by putting in different dopants and impurities. And actually the same is true of the nanotube structures and also graphene. You can start to put impurities in and play around with the properties. But I think that's pretty much all I want to say. I know it's quite late, so thanks for sort of staying with me for the hour. Hopefully I've given you a kind of something to, there's parts of that talk that you've got interested in, or parts of that talk that made you think more about aspects of science. This is actually a picture supposedly of me. We had an artist in residence who came into the department and worked in the department for many months, and she came to have a chat with me about what I was doing. And then she came back the next day and said, I've drawn a sketch. So this is me, the Queen of Diamonds. This is my cycle helmet. I told you I'm a keen cyclist. So yeah, she was inspired by the diamond work that I do. But yeah, thank you for listening, and I'll try and answer any of the questions that you have. And I think I'll leave it at that.
Excellent. Well, thank you very much, Julie, for that excellent talk. And we have had quite a few questions actually, so I'll start by reading out some on the list. So if you do still have a question, please feel free to put it on the chat list here. So first of all, I think they are in order of your presentation actually. So first of all, on the slide regarding potential uses of fullerenes, this person was wondering how electron acceptors links to the photovoltaic solar cells that were mentioned. So that link.
So I think, as I said, this isn't necessarily my area of expertise, but I think when you're looking at photovoltaics, you have to match electron acceptors with electron donors in order to get splitting. And so you're always looking for materials that can either very good at accepting electrons or materials that are very good at donating electrons in order to complete your electrical circuits. So yeah, whenever you read about photovoltaics, you'll always see that you're looking for materials that match on those types of properties.
Excellent, thank you very much. One medicinal question here. How does nanotube trap drugs and deliver them? So what's the kind of mechanism for encapsulating pharmaceuticals?
So for nanotubes, so this is quite an interesting question. So nanoparticles and nanotubes, people were worried. So people talked about using these things as drug delivery agents. So they're tiny. And so you can maybe functionalize the outer surface of the nanoparticle or the nanotube using chemical linkers with your drug molecule of interest and try and deliver it into the body, or try and get it to get across the membrane in a cell. The problem is, so people proposing all of this, and then everybody started to get worried. Well, because I'm sure you've all heard of asbestos and inhalation of particles and things like this. And people then started to get concerned about what are the health risks actually of working with nanoparticles and nanotubes. So there's two sort of schools of thought. There's the people that say, yes, this is very good. And actually we can use them because they're so tiny to functionalize them and to deliver sort of drugs into the body. But there's also a school of thought that said any work that goes on in that area, you have to also do hand in hand with the health and safety implications. So there's lots of tests being done in both avenues in order to make sure that what we do is safe.
Excellent, thank you very much. One interesting part here about growing carbon nanotubes. So how do you actually manipulate them to get the structure that you desire?
Okay, so that's a good point. So you saw that the nanotubes grow from like metal nanoparticles. And so if I want to make them all stand up like this, what I have to do is I have to put lots of tiny nanoparticles all really, really close together. Because what happens is as soon as the nanotubes start to grow, they tend to grow up, and if they get too big, they can start to flop down. But actually, if you can get them all growing really close together, because of the very high van der Waals forces of interactions, they kind of stick together, and so they all keep growing up and up and up. If I want to grow them so they grow across the surface like that, that's quite challenging because, you know, if you have a high density, they tend to want to go up. So what we tend to do is you can put electric fields. So you use electric fields to perhaps try and force them. So you've got another energetic force going in to force them in this direction and not up here. Or I can use a substrate that actually energetically they like to lie across. So there's, again, favorable energetic interactions. And in science, everything always wants to go down the path of least resistance. So you have to design your system to do it. But it's really clever thought experiment, actually. So you can, in principle, make whatever you want, but you have to think about, how do I have my catalyst? Do I need other things in there to try and force them in a particular direction? Then obviously, if you want to grow isolated tubes, you have to have a very low density of your catalyst. So all of these things go in, and that's why it's so interesting, actually, with nanotube growth and manipulation.
Excellent, thank you very much. And talk about the growth of graphene. You mentioned about growing the kind of layers of graphene.
Yeah.
A question here about what is it? What feature of a metal affects the layer growth? For example, why is it that copper makes single layers and not multiple? What's the...
Yeah, that's a really good question, and I say we don't do much work on graphene, and I'd have to my student left and created a company that was working on doing all this stuff. I'd have to go back and remind myself of the differences for why that is, but there's a self-limiting mechanism on the copper, and I can't remember what the particular property of the copper is that makes it do that. So it is a really good question. So what I'll do is I will go back and I will, we can maybe post it onto the forum website, or if there's something like that, I can put that up. Or actually, I tell you what, why don't the person who asked that question, can you email me? And I will let you know tomorrow, because I know where to look for that information, because I have the paper that describes that. So whoever asked that question, drop me an email at j.macpherson@warwick.ac.uk. and I will reply to you tomorrow.
Excellent. Thank you very much for offering to do that. There's a couple of questions about diamonds. I kind of group a few together. There's quite a few that talk about the differences, and the general gist is that, well, if we can synthesize or make the diamonds, why are we still digging them out of the ground? Is there any difference between a synthetic diamond and a naturally occurring diamond?
So this is a big philosophical question, right? So diamonds have always been associated with wealth, I think, and, you know, a sense of, you know, if I get to a certain status in life, I'm gonna buy myself a diamond, or, you know, if you love me enough, you're going to give me a diamond ring, that kind of thing. And in a sense, that's bred people. People buying them have bred that, right? And then it comes down to, well, the first question is a natural the same as a synthetic? Absolutely. The only difference would be in that perhaps the way that the defects go in, or the impurities, are under a much more controlled method. But in terms of the quality, when you assess diamonds, I think it's the 5 Cs or 4 Cs, they're exactly the same. So you're buying the same thing. In fact, I'm wearing a blue diamond that I bought that was grown for me in a lab in Russia. And I don't have a problem with buying a synthetic over a natural. And actually now the diamond companies, rather than mining them, are realizing this, and they're producing more and more synthetics. But it comes down to you, you're buying them. So if you continue to buy naturals, there will be a demand for them. And if you pay the price for them at that cost, there will be the demand will keep up. But if people decide to make the switch to more ethically viable synthetics, then there's definitely, people are now producing these as jewelry. But the question is, people will say, well, do you want something grown in a lab, or do you want something that's been, crafted by Mother Nature over like hundreds, thousands of years? And again, it's all a psychological thing. As a scientist, I want to wear a synthetic, right? I really like the idea of wearing a synthetic, and I wear it just because I do research on this diamond anyway. It's just, for me, it reminds me of what I do. But it's a really good question. And it throws up a lot of sort of questions, I think, further questions on that.
Thank you very much. On a similar vein, if you can actually synthesize the different colors by the doping and these, and of course it's amazingly small concentrations have such a large optic effect. And I guess also, if you mentioned the vacancies, you can perhaps create those by irradiating the diamonds. Different ways of doing it. Is there a technique that you can actually differentiate between of the same concentration of defects, a natural diamond, as it were, and one you synthesize? Is there a difference in the way the defects are arranged, or
yeah, you're completely right, Mark. So the diamond companies work with scientists in universities because they have to be able to differentiate between a synthetic and a natural. And it is down to how the defects align. The defects are much more ordered in a synthetic than in a natural, and you can pick that up using different techniques. Because at the moment, there is a big price discrepancy from buying a natural and buying a synthetic. So a lot of people are going to be perhaps synthesizing synthetics and passing them off as naturals. So people have to use clever science to differentiate. And so the scientists are ahead at the moment because they can differentiate, but the growers are trying now to grow in a way that matches more and more like a natural. So it's a game.
I imagine there's fascinating area, actually. Just have a look through a couple of questions, a few final ones. So obviously you mentioned that the dope diamonds, or those that dope boron, were conducting. So I asked, why do you use the black diamond in your research to conduct electricity instead of other colored diamonds? Is there a preference?
Yeah, okay, so you need to, so what happens is, I want my black diamond to behave like a metal wire. So it conducts electricity really easily. The problem is that if you, so remember I said that as you start to put your dopants in the blue, it starts to go from blue to black, and that's telling me, so I can by eye kind of spot how much dopant is in my diamond. You need to hit a particular dopant threshold in order for it to sort of go from low conductivity to high. So effectively, if you're you're familiar with the terms, to be semiconducting all the way through to metallic. And boron is the only one that you can get into the diamond at high enough concentrations to be fully metallic. Nitrogen you can get in, but you can never get enough in, just because of how it's going into the lattice. It doesn't sort of just pop in like the boron does. It goes into a different orientation. So it's your only option. If you want to use diamond as an electrode or as like a metal wire, you have to use black diamonds.
Excellent, thank you very much. And I think just one final one to end on. Obviously, excellent talk, generating so many questions here. This is brilliant. In terms of making synthetic diamonds, are there any limitations, and could there be some properties that we haven't discovered yet when we make?
Well, that's really neat, actually, and I think. So are there any limitations? So size at the moment, right? Size is a big thing. So people want bigger and bigger slabs of diamond to grow. And at the moment, so you can grow diamonds in a polycrystalline form. So that means you're growing it with lots of different crystal facets. For many applications, you need to grow the perfect single crystal. And to do that in a large volume at the moment is challenging, but that's coming. I think, and again, it's not necessarily 100% my area, but I believe that all the stuff I was showing you on this NV defect, and if you put in diamond and quantum computing, you'll see that this is one of the front runners for the next generation in fast computing, is that has come about because of the synthetic ability to play around with how much nitrogen and vacancies you've got, just as you said, by radiation or things like this. And that probably would never have happened naturally, because you didn't have the way to manipulate defect density and vacancies in the way that we can in the lab. So that's why actually I find diamond so fascinating, because you can play with its properties. And as I said, it was picked up by the UK government as like, this is a real thing to watch in the future. And for myself, who developed sensors, I can put diamond, because it's diamond, into environments where other sensors would just get eaten away. You know, like in nuclear reactors, I could put them into nuclear reactors. I can put them into, you know, very acidic environments in sort of waste streams for like environmental monitoring. It's a fantastic material to play with. And that's what I've been really working on predominantly for sort of the last 5-10 years.
That's fantastic. Thank you so much for sharing that with us. And clearly your passion for the research comes through, which is wonderful. If I'd like to pass over now to Jill to say a few words and to thank our speaker. Thank you so much.
Thank you, Mark. And can I say a big thank you on behalf of us all to you, Julie, for that excellent talk. It was very clear to follow, very informative and very up to date, which I think is very interesting, especially for the younger the students here, because they will be involved in that kind of area or in current research, hopefully in the future. So very interesting and very informative. Thank you very much from us all. Thank you.
Oh, my pleasure. As I said, if the person who asked me the graphene question, if they do come, please drop me an email, because I do want to answer that.
She has actually said on the chat, she said, yes, I can, I will email. And
thank you. Okay, perfect. No, definitely, because I do know the answer to that, but I just need to remind you. So I just want to, before I say it, because this is being recorded, I want to double check I'm going to tell you the right thing.
That's one, and there are quite a few messages of thanks as well coming through the chat. So
okay, my pleasure. Well, I hope people enjoyed it, because it was like, you know, it's 7 till 8 o'clock at night. You've all been working hard, but yeah, and if anybody has any more questions, I can go into a bit more detail with you by email and things like that. So I'm really happy if you want to drop me an email.
That's wonderful. Well, thanks once again, and thank you all for joining us as well. As Julie said, I know you've had a hard day at school and all the extra online learning that you're doing as well. So thank you all so much. So do check our website for the next series of lectures. The next one will be in a fortnight's time. And as we mentioned, this will be this has been recorded, so we'll just edit it slightly and put it in a format that you can access it via the WMCT website. So thank you all very much. So if you would like to leave the Zoom call, I think the committee members just hang on just a quick few words. But thank you all very much, and hope to see you in a fortnight's time. Thank you.